hardly 2 or 3 labs we have. I think one is in Japan, maybe, I don't remember exactly, and one which is in US, or one more somewhere else. There is one more lab, and they have set up these labs. They are very, means actually it is very difficult to set up these labs. Very difficult. Okay, so we will start with the neutrinos, and we have already done the beta decay. तो बीटा डीके में आपके पास जो इक्वेशंस थे, just let me share the. So today we will not have very much derivation kind of thing. तो आज ऐसा नहीं रहेगा कि बोर हो रहे हो, बोर तो हर रोज ही होते हो, बट थोड़ा सा लगेगा कि मे बी समथिंग we come to know about these things. Okay, so let me first write the beta process. So beta process हमारे पास क्या था? A neutrino, a neutron could decay, और एक अगर nascent neutron है, ये means free neutron, it hardly have a life of 10 minutes. 10 minutes के बाद वो decay हो जाता है. एक सेकेंड. So that was making a proton plus, this is 0 charge, this is +1 charge, so obviously the electron will have to be -1, so total is this one, and we have a anti-neutrino which is coming from this particular reaction, and a proton which can be decayed as neutron. This is a plus charge and this is a 0 charge, so we need a positron which is a plus charge, so this charge is balanced and we have a neutron. So electrically balance करने के लिए neutrino की need नहीं है, but for other things, that is something like a spin, energy, momentum, all these things, you need these particles. So what could happen, because a neutrino when decays it produces a neutron when decay it produces an anti-neutrino. So is there any possibility that if anti-neutrino combines with proton, then what could be the result? Means you are not producing an anti-neutrino, but you are combining an anti-neutrino with a proton. So if a neutrino is coming from somewhere and a proton, it get hits with the proton, direct hit, and do a reaction, then what will happen? So there is a possibility that a neutron could be produced, because there is this mass is more, obviously इसका mass ज़्यादा है proton से, ये massless particle है, but it has energy, so that energy can be dumped in the form of mass to the proton. This is a possibility. So proton, which is a lighter mass, and neutron, which is a heavier mass object, so that can be created because you have an extra energy, and that energy can be dumped in the form of mass. And due to charge balance, we have to have this particle also. And similarly, if you have this kind of reaction, means if you have a neutrino, which is a normal neutrino, when it interacts with a neutron, then what could happen? A proton could be made, and with charge it should be this one. So these are the possible reaction they have thought. This is something like a called as these are beta decay, and these are called inverse beta decay. रिवर्स ऑफ बीटा डीके. तो आपके पास न्यूट्रिनो जनरेट हो रहे थे बीटा डीके में, अब आप न्यूट्रिनो को यूटिलाइज कर रहे हो एंड यू आर बम्बार्डिंग विद प्रोटॉन एंड न्यूट्रॉन एंड यू कैन गेट दीज थिंग्स. But we never get this kind of reaction, and this is interacting with this one. We don't have this kind of reaction, and these have been tested. ऐसा नहीं कि इसको सिर्फ ऐसे ही कह दिया कि ये रिएक्शन पॉसिबल नहीं है. अगर हम न्यूमेरिकली चार्ज कंजर्वेशन से देखते हैं, या मोमेंटम कंजर्वेशन से, या एंगुलर मोमेंटम कंजर्वेशन से, तो दिस कुड बी पॉसिबल रिएक्शन. अगर this could make a proton and this is a 0 charge and there could be a minus, so this is possible. इसमें कहीं कोई गड़बड़ी नहीं लग रहा है, सब कुछ ठीक है। अगर आप मोमेंटम देखोगे स्पिन तो वो भी बैलेंस हो रहा है। आप अगर दोनों पर हाफ हाफ है, यहाँ पे भी हाफ हाफ, तो दैट इज बैलेंसिंग, चार्ज इज बैलेंसिंग, इवन एनर्जी कुड बी बैलेंस्ड, so everything is balanced. But these reactions are not seen. It means apart from other parameters or other characteristics what neutrino have, for example mass, spin, their motion, how they move, means they move like a something like a speed of light, or they have behave in a such a way, they have mass, they don't have charge, so these things are very common. They have spin half, both have spin half, but something there is a difference between these two, यानी दोनों सेम नहीं है। अगर ये रिएक्शन पॉसिबल नहीं हो रहा है, इट इट मींस कि सेम, बाकी सारी प्रॉपर्टी सेम है, बट समथिंग इज डिफरेंट इन दीज टू पार्टिकल्स, दे आर डिफरेंट। क्योंकि हम हमारे जो स्टार्टिंग में जब व्हेन द न्यूट्रिनो वर डिस्कवर्ड, दे आर चार्जलेस, और चार्जलेस रीजन के कारण हमारे पास उसको एक एंटी पार्टिकल और पार्टिकल के फॉर्म में डिस्टिंग्विश करना डिफिकल्ट हो रहा था। कि हमारे पास है ना, प्रोटॉन का एंटी पार्टिकल क्या है, माइनस पी वाला, इलेक्ट्रॉन का एंटी पार्टिकल प्लस वाला है, एंड सो ऑन। सो वी whenever there is a charge we can easily assume कि there will be anti particle, बट जिसके पास चार्ज नहीं है उसका एंटी पार्टिकल क्या होगा, दैट वाज द क्वेश्चन। दैट वाज वेरी डिफिकल्ट थिंग कि भाई चार्ज नहीं है तो एंटी पार्टिकल का मीनिंग क्या है, बाकी सारी प्रॉपर्टी तो सेम है, चार्ज भी एक जैसा ही है, स्पिन भी सेम है, सब कुछ सेम है, एवरीथिंग इज सेम, बट स्टिल देयर इज अ डिफरेंस बिटवीन दीज टू, because we don't have this kind of reaction, we have this kind of reaction, and they are called inverse beta decay. Okay, so what was the first thing that they have to do, कि सबसे पहले तो इसको डिटेक्ट करना है, अगर ये है तो है कहाँ पे, if it is there, where it is, and how we will capture this. If I want to catch means, जब तक आप देखोगे नहीं, you cannot say कि that is existing. सिंपल है ना, अगर हम किसी चीज को नहीं देखते हैं तो हम ये नहीं कहते कि एग्जिस्ट कर रहा है। जब हम देख लेते हैं, मेजरमेंट करते हैं, when we get the results according to our prediction, then we can say yes, that is there. So Pauli has predicted कि ऐसा कुछ होगा, and theoretical foundation was done by the Fermi, so that is why it is named by the Fermi, and these are neutrinos. So Fermi ने उसका derivation भी कर लिया था, सब कुछ कर लिया था, probability निकाल ली थी, सब कुछ कर लिया कि how you can find what are the wave function, what is the parity of these particle if they are emitting from somewhere. Everything was done, but still the detection is not there because they are very light particle and they don't have charge. So it is very difficult to capture those particles. Photon को capture, photon भी light particle है, its stress mass is 0, but it can be captured because it is easily absorbed by something and emitted by something. So that was very easy. But these particles neither get absorbed by any particular substance or not even being emitted easily by any. It is emitted, but we don't have any absorption. So absorption इसका बहुत ही low है, मतलब it can go from the sea of proton without interacting. पूरा प्रोटॉन से आपने फिल कर दिया एक रूम, और आप न्यूट्रिनो पास कर रहे हो या एंटी न्यूट्रिनो पास कर रहे हो, बिकॉज एंटी न्यूट्रिनो इज गोइंग टू इंटरेक्ट विद द प्रोटॉन, एंड इफ यू ट्राई टू सी कि भाई इतने सारे प्रोटॉन है, प्रोटॉन मैंने बिलियंस ऑफ प्रोटॉन फिल कर दिए हैं, तो कोई ना कोई तो कैच करेगा, किसी न किसी से तो रिएक्ट होगा, इट डजंट रिएक्ट. सो बाय द डेरिवेशन what they have found that if you do a reaction with these this particular, let us focus on this reaction. We are focusing on this reaction. This is plus, so this will be plus. This is 0. This is plus charge. This is 0 charge. So we focus on this reaction. So theoretical calculation can be done and we can find the sigma. Sigma मैंने पहले भी कई बार एक दो जगह आया है, अभी तक हम उसका डेरिवेशन नहीं किया, ये है क्या सिग्मा, exactly we have not done that, because that we will done in the nuclear reactions. जब न्यूक्लियर रिएक्शन करेंगे तो वहां पे हमारे पास सिग्मा का फॉर्मल अंडरस्टैंडिंग हमारे पास डेवलप होगा कि है क्या सिग्मा एंड हाउ वी कैलकुलेट एंड व्हाट इज एक्चुअली द सिग्मा इज. सिग्मा मैंने लेकिन पहले भी आपको बताया है, तो एक बार जरा मुझे फिर से बताओ कि सिग्मा है क्या, व्हाट इज द सिग्मा इज. इफ आई हैव समवेयर आई हैव गिव द रेफरेंस ऑफ सिग्मा, तो कुछ एक आइडिया दिया होगा मैंने. कि सिग्मा है क्या, and we can calculate the sigma also. Theoretically we can do the calculation. There is a equation for that, there is a formula for that. So sigma हमें क्या आइडिया देता है, सिग्मा की यूनिट क्या है और आइडिया क्या देता है? यूनिट बता दो पहले मुझे, यूनिट मैंने कहीं ना कहीं लिखा होगा, इट्स यूनिट, किस यूनिट पे मेजर होता है ये, याद है नहीं याद है? Because you may be coming from some different planets, so you may not be aware what is sigma is. You may have different alphabets. बताओ सिग्मा क्या है? ये यूनिट कभी मैंने बोला पहले, सेंटीमीटर स्क्वायर, ये यूनिट कभी पहले सुना है? ये हमने किया है, पक्का किया है, ऐसा तो नहीं कि नहीं किया है। यस और नो? इसका नाम बता दो, चलो नाम ही बता दो, छोड़ो सिग्मा का यूनिट छोड़ दो, नाम बताओ, नाम भी मैंने कई बार बोला होगा, इफ यू रिमेम्बर। गूगल से देख के बता दो, कहीं से भी देख के बता दो। हम्म, प्रोबेबिलिटी पर target nuclei, you can say atom also, for the reaction to occur, divided by, ये फॉर्मूला मैंने नहीं बोला लेकिन आपको मैंने हिंट दिया होगा कि इसका मीनिंग क्या है। हाँ, पता चला गूगल से क्या नाम है इसका, कॉमन नेम क्या है सिग्मा का? ये नहीं, यस नो कुछ बताओगे तभी तो आगे बढ़ेंगे हम, कि कॉमन नेम क्या है सिग्मा का? नो सर, मैंने क्लास में कई बार बताया है, और मैंने ग्राफ में ज्यादातर बताया हुआ, ग्राफ मैंने एक्स एक्सेस या वाई एक्सेस का बनाया, तो वाई पे मैंने मैक्सिमम टाइम लिखा होगा, कि वाई पे हम नंबर ऑफ पार्टिकल्स लिखते थे, उसको मैं कई बार सिग्मा बोलता था, उसका एक नेम भी आता है, तब बीच में कई बार मैंने बोला होगा। सेंटीमीटर स्क्वायर किसका यूनिट होता है? सेंटीमीटर स्क्वायर किसका यूनिट होता है? एरिया होता है। तो दिस इज समथिंग लाइक एरियल यूनिट एंड इट इज क्रॉस सेक्शन। क्रॉस सेक्शन भी एक एरिया होता है, आप किसी को कट करके देखते हो तो आपको जो व्यू होता है वो उसका एरिया व्यू होता है, दैट इज अ क्रॉस सेक्शन, और इन पर्टिकुलर इट इज कॉल्ड रिएक्शन क्रॉस सेक्शन. So the reaction cross section is something like a probability per target nuclei, means there is a target, and for every target nuclei what is the probability of having a reaction. रिएक्शन होने की प्रोबेबिलिटी क्या है? जैसे अल्फा का था, अल्फा का भी हमने कैलकुलेट किया था ना, प्रोबेबिलिटी टनलिंग कोफिशिएंट, और टनलिंग टी की वैल्यू या प्रोबेबिलिटी दैट वाज समथिंग व्हिच इज 10 टू -90, वेरी स्मॉल. तो टू गेट आउट फ्रॉम द न्यूक्लियस the alpha particle have this much of probability when it hits a boundary. So every time it has that much of probability. In same sense, this is also something like a, that was also the same thing, वो tunneling probability उसको हम कह देते हैं वहां पे, but वो out होने की means to get out from the nucleus, that is a probability. Here also, to get interact or to have a reaction with any target nuclei, this probability is uh, whatever the probability you get divided by how many particles have been incident. आपने कितने पार्टिकल इंसिडेंट किए और आपकी रिएक्शन प्रोबेबिलिटी क्या है, इन दोनों का रेशियो जो है दैट इज रफली व्हिच इज सिग्मा. इन डिटेल वी विल डील विद दिस इन द when we do the nuclear reactions. So by theoretical calculation, this number was roughly 1.2 into 10 to the power of -19 बाण. एंड बाण हमारा यूनिट क्या है? बाण की 1 बाण की वैल्यू होती है 10 to the power of -24 centimeter square. So this number is roughly 1.2 into 10 to the power of -43 centimeter square. It is zero. It is nearly zero, less than a Planck constant. Planck constant -34 तक जाता है, ये और 10 orders नीचे जा रहा है. तो this is a reaction probability, means you can imagine that out of whole of the proton, इसको दूसरे सेंस में imagine करो, this is a proton and a neutrino is getting, means hitting this particular proton. And what is the chance to get embedded within this or do certain things and get a decay into certain form? Means for some time they can embed themselves, means neutrino can enter into this one and they have certain rearrangement and they can emit as a neutron and a electron. So that is a positron, that is a possibility. तो एक न्यूट्रॉन और पॉजिट्रॉन जनरेट हो सकते हैं. But if you divide this proton into 10 to the power of -43 times, so out of that smallest area of the proton, it can interact with. तो आप क्या करो, प्रोटॉन को इतने पार्ट में डिवाइड करो, उसमें से एक पर्टिकुलर स्मॉलेस्ट डिवीजन अगर आपका न्यूट्रिनो उसको हिट करता है तो रिएक्शन हो जाएगा. दिस इज व्हाट यू कैन अंडरस्टैंड इन द अदर सेंस कि एक डार्ट है, डार्ट आपका न्यूट्रिनो है, आपको हिट करना है, लेकिन जो प्रोटॉन है, प्रोटॉन में आपने उसको कितने पार्ट में डिवाइड कर दिया? 10 टू द पावर ऑफ +43 पार्ट्स में आपने इसको +43 पार्ट्स में आपने उसको डिवाइड कर दिया. And you are saying that this one is the part where you have to hit the dart, which is hardly possible. तो उस 10 to the power of 43 टाइम्स आपने डिवाइड करने के बाद फिर एक पॉइंट को आपने फिक्स कर दिया कि इसी पॉइंट पे आपको डार्ट को हिट करना है. तो which is very difficult. You cannot do, at least in your lifetime you cannot do that. This is not possible. So this was very small. It is hardly a number. And this was the reaction cross section of a neutrino. If you do the calculation, it means if I have a sample and in that sample, if I means when the neutrino, which is being going to a target, and the target is something like this one, a box, and you have a flux of neutrino, we are hitting that neutrino. And in this particular box, what you have done, you have kept how many? 10 to the power of 24 protons per centimeter cube. This is the density. कोई ऐसा मटेरियल आपने देखा है जिसमें इतने प्रोटॉन्स पर सेंटीमीटर क्यूब होते हैं? Have you seen any material, or if you know any material which have 10 to the power of 24 protons per centimeter cube? If someone answers me, I will Paytm or transfer 2 rupees to his account to get a chocolate. If you give me a good, if you give me a correct answer. Do you know any material which have this much of proton per centimeter cube? I will transfer 2 rupees. बोलो क्या बोल रहे थे? क्या पॉसिबल नहीं है? 2 रुपए क्यों नहीं ट्रांसफर हो सकते हैं? पॉसिबल है.
No sir, any material can be possible because in a centimeter there are a very large number of atoms and there are very large number of protons.
Okay. Any material could be of this order of proton. Very good, very good answer. Water is that material. जरा water ले लो और heavy water ले लो, so that is a material, and that will have this much a number of proton. If you calculate per centimeter square, per centimeter cube, how many atoms are there? You just calculate, you will get a mole. 1 ग्राम 18 ग्राम वाटर लेते हो तो 18 ग्राम वाटर में क्या है आपके पास? 1 मोल ऑफ H2O। H के पास इतने सारे प्रोटॉन है, एक प्रोटॉन H के पास है, दूसरे H के पास है, और 8 प्रोटॉन्स आपके ऑक्सीजन के पास है, तो आपके पास 10 प्रोटॉन्स तो यही हो गए। 18 ग्राम ऑफ वाटर हैव 1 mole of water molecules, and every molecule have at least 10 protons. So 10 into 1 mole is 10, 623, or 6 point something into 10 power 23 है. You just make it multiply with 10, so you will get 10 to the power 24. So we have any material you can have this number. So very good. किसने बताया मुझे बता देना, डोर पे मुझे भेजने। ओके, चैट बॉक्स में लिखना बाद में। Okay, so if you have these number, means water is a good candidate, and if you have a heavy water,
आपने
हाँ बोलो
सर सिग्मा के न्यूमरेटर में क्या लिखा है आपने?
सिग्मा के न्यूमरेटर में कहाँ है?
डिनोमिनेटर में।
अच्छा, फ्लक्स है, फ्लक्स, इंसिडेंट फ्लक्स means number of neutrino per unit area per unit time. Flux is per unit area per unit time. ये वाला कह रहे हो ना, this one?
यस सर।
इंसिडेंट फ्लक्स है वो। तो किस रेट पे हमारा न्यूट्रिनो एंटर हो रहा है, दैट इज आल्सो देयर। ओके, सो वी आर श्योर कि कोई भी मटेरियल हम यूज कर सकते हैं टू कैप्चर अ न्यूट्रिनो। वी कैन हैव दिस मच नंबर ऑफ प्रोटॉन, व्हिच इज वेरी गुड अमाउंट, व्हिच इज नॉट अ वेरी पुअर थिंग, व्हिच इज वेरी गुड अमाउंट। It means if I travel, means if a neutrino, antineutrino travels 1 centimeter in this particular material, which is having this much of density, which is very good density, then the probability of getting captured will be sigma into this number, which is 10 to the power of 24, because this number is centimeter and this number is per centimeter cube. If you have this means this unit is centimeter square and this unit is centimeter inverse, cube में हो गया, inverse में। So it means 10 to the power of minus 19 is the probability per centimeter. Yani every centimeter when you travel, this is a probability of getting captured for a neutrino. क्योंकि ये तो उसका सिग्मा है और हर एक टाइम पे इतने को एनकाउंटर कर रहा है पर सेंटीमीटर में। तो इफ इट travels in a material which is having this kind of density, so every centimeter the chance is this one, for every centimeter. It means to have a chance 1, अगर मेरे को न्यूट्रिनो को कैप्चर करना ही है फाइनली, तभी तो मैं डिटेक्ट करूंगा। जब तक मैं उसे कैप्चर नहीं करूंगा, आई वोंट बी एबल टू डिटेक्ट, मींस आई हैव टू स्टॉप द न्यूट्रिनो विद इन माय मटेरियल। It means neutrino has to travel 10 to the power of 19 centimeter in that material, so that when you multiply these two numbers, you get answer as 1, means 1 neutrino is going to capture. And what is this number is? 10 to the power of 19 centimeters. What is this number? This number is roughly 10 light year. इसीलिए the sun neutrino, when sun emits a neutrino, that is actually called as fusion neutrino, because fusion reaction is going on and the neutrinos are emitted. और जब फ्यूजन रिएक्शन होता है जिसमें आपके पास एंटी न्यूट्रिनो के एमिशन की पॉसिबिलिटी होती है, जब भी फ्यूजन रिएक्शन होता है, यू हैव अ न्यूट्रिनो. सो दोज न्यूट्रिनो गेट पास फ्रॉम द सोलर सिस्टम आल्सो, एंड इवन समटाइम दे गो पास फ्रॉम द मिल्की वे आल्सो. तो सन के न्यूट्रिनो मिल्की वे तक को क्रॉस कर जाते हैं विदाउट हैविंग एनी इंटरेक्शन, बिकॉज दिस इज द इंटरेक्शन रिच. इतना डिस्टेंस ट्रैवल करने के बाद देयर इज वन चांस कि वन ऑफ द न्यूट्रिनो गेट being captured. So that is why they are so amazing. They just travel, they cross the earth, they cross the Jupiter, they cross the Saturn, and they just go away without any interaction. And we are getting good amount of flux of neutrino from the sun. There are billions of reactions are going on in the core of sun, and every time a shower of neutrino is coming out, but still we don't feel those neutrinos. When we are sitting at this time, we some of the neutrinos are passing from us also, but without any interaction, without any means any harmful effect you can have. हार्मफुल इफेक्ट वही मटेरियल करता है जो इंटरेक्शन के साथ मूव करता है. गामा हो गया, अल्फा तो नहीं करता है, बीटा डीके कर सकता है आपको हार्मफुल. इट इज अ हार्मफुल रेडिएशन. गामा इज अ गुड हार्मफुल रेडिएशन, or any other high energetic particles is a, but this is also high, but they don't interact, so there is no harm. So this is the, it means it is very difficult. You cannot make a lab of this much of size. It is not possible. This is not possible. So what is one thing which is possible, that या तो आप क्या करो कि 1 सेकंड में न्यूट्रिनो को कैप्चर कर लो, यू मेक अ लैब ऑफ 10 लाइट ईयर, और आपने करना ही करना, आपको न्यूट्रिनो मिलेगा ही मिलेगा. देयर इज नो चांस कि न्यूट्रिनो वहां से बच के निकल जाएगा. इट हैज टू इंटरेक्ट with one of the proton, and you will get the deduction. But this is not feasible. The other thing would be wait for a longer time. आप क्या करो, आप डायमेंशन छोटा ही लो, अपने लैब का डायमेंशन छोटा रखो, बट आपको वेट बहुत करना पड़ेगा. 1 साल नहीं, 2 साल नहीं, 10 साल, 20 साल, 25 साल, 30 साल तक वेट करें, मीन्स 30 years. The first neutrino after setting up the lab means it took 5 years, around 5 years, 4 or 5 years, then they got the result. And to set up a lab it took around more than 10 years, because उस समय कुछ आइडिया भी नहीं था कि क्या रखें, कैसे रखें, कहाँ से लेके आए. बट atom bomb was discovered, and first time the 1945 the fission reaction was able to be done on the planet. पहली बार हुआ वो reaction, और उस reaction का outcome हुआ कि it has a shower of anti-neutrino. So in 1950s there are so many labs around, even after 2 years, 2 to 3 years, there are so many area where the fission was used as a nuclear reactor. Means it was the basic process in the nuclear reactor. तो nuclear reactors बनने शुरू हो गए, रशिया में बनने शुरू हो गए, यूएस में बनने शुरू हो गए. तो दोनों कंट्री में बड़े धीरे धीरे, क्योंकि स्टार्टिंग में तो बॉम्ब के फॉर्म में यूज हुआ था, उसके बाद उन्होंने इसको बेटर यूज करने के लिए दे कन्वर्टेड इनटू अ न्यूक्लियर रिएक्टर वेयर इट वाज अ कंट्रोल्ड फिशन रिएक्शन. And in that controlled fission reaction we have a emission of this. So there was a source, means on the earth we have a source of anti-neutrino. और दूसरे सोर्स क्या थे, जो सन से आ रहे हैं, जो कि न्यूट्रिनो है, दे आर ऑलरेडी कमिंग, बट उनका थोड़ा सा फ्लक्स वैल्यू कम हो जाता है. और इफ यू आर नियर टू एनी न्यूक्लियर रिएक्टर द फ्लक्स इज गुड. जो न्यूक्लियर रिएक्टर के अगर आप पास जाते हो तो फ्लक्स आपके पास ज्यादा स्ट्रांग होता है इसका एंटी न्यूट्रिनो का. बट सन से जो आ रहे हैं उनका फ्लक्स धीरे धीरे डिक्रीज, बिकॉज इट इज स्फेरिकली डिस्ट्रीब्यूटिंग ना, तो स्फेरिकली इन ऑल डायरेक्शन इट इज कमिंग आउट. तो एज द एरिया इंक्रीजेस द फ्लक्स वैल्यू डिक्रीजेस. आप पर यूनिट एरिया की वैल्यू करोगे, देखोगे तो आपके नंबर ऑफ न्यूट्रिनो दे गोज ऑन डिक्रीजिंग एज यू मूव अवे फ्रॉम द सन. So that is why they focused on the nuclear reactor. And from the nuclear reactor we are getting anti-neutrino, we are not getting a neutrino. Means you can do this reaction which I have written, this one. That is anti-neutrino plus proton, and they are giving us a neutron and a positron. Okay, so till now are you able to understand what I am saying, या कुछ भी नहीं समझ में आ रहा है? अगर है तो फिर हम आगे बढ़ते हैं. How the experiment was performed and how the detection was done. तो डिटेक्शन और एक्सपेरिमेंट क्या है उस पर हम चलते हैं. बढ़े आगे.
Yes, sir.
Yes, sir.
So at least we are what till now what we have got ki neutrino are very least reactive, they don't react easily. And if you want to have a reaction, either you have to make a lab which is of a 10 light year long distance, which is not feasible, or you can have a lab which is very small, but you have to wait for a time कि कभी एक reaction हो जाए. Okay, so the lab what they have set up, and the person where Davis, no, Rennies and Count. Davis we had done other thing. Rennies and Count. Rennies and Count. Okay, so what they have done, and they have published around in 1954. They have started the lab in 1950, and around 1954 or 1953 में they have done कि भाई हमारे पास एक कुछ result आए हैं और they must be a candidate for a neutrino, where that we have captured the anti-neutrino. So what they have, I have not made the animation, but इसका animation बन सकता था, but मेरे पास time नहीं था. So they have took a tank. In that tank, we have H2O, which is actually a heavy water, and there was cadmium chloride also, CdCl2. बिकॉज वर्ल्ड वॉर के बाद बहुत सारा काम होने लग गया था न्यूक्लियर फिजिक्स में, बिकॉज एनर्जी वाज सो बिग. इट टुक हार्डली अ ग्राम्स ऑफ यूरेनियम और प्लूटोनियम एंड यू कैन हैव सो मच ऑफ एनर्जी. तो टीएनटी को क्रॉस कर गया था. टीएनटी, यू नीड वेरी गुड अमाउंट ऑफ टीएनटी टू हैव दैट काइंड ऑफ एनर्जी. और छोटा सा यूरेनियम, बिल्कुल हार्डली ग्राम्स ऑफ यूरेनियम, you have same energy, which is very huge, and tons of TNT you need to produce that energy. So people have started doing यार ये बहुत अच्छी चीज है और this is very goodful, means it is fruitful, very good, very good. मतलब starting में तो मान के चलो जो peak था ना, that was around 1950 or 55, और उसके बाद से decline होना शुरू हो गया और आज तक वो फिर से peak नहीं आया on the work of nuclear reactors. Still the nuclear reactors are there, but अभी भी एटलीस्ट इंडिया को अगर देखोगे तो इंडिया में हार्डली 2%, मे बी लेस देन, आई डोंट एग्जैक्टली डोंट रिमेंबर, बट अराउंड 2% और लेस देन 2% एनर्जी इज प्रोड्यूस्ड बाय दीज रिएक्टर्स. वेरी वेरी लेस. कुछ कंट्री में है, दे हैव डन अराउंड 30 to 25%, बट स्टिल वी हैव नॉट शिफ्टेड 100%, एंड दैट इज नॉट फिजिबल आल्सो. दैट इज नॉट फिजिबल कि 100% आपका जो पावर है वो उसी से आ रहा है, बिकॉज इट इज हार्मफुल, इट इज वेरी हार्मफुल आल्सो. इफ समथिंग हैपेंस, जो कि 2 बार आपके पास, मेरे ख्याल आपने जापान वाला आपने देखा ही होगा, अभी कुछ दिन पहले ही था, 3 साल या 4 साल पहले की बात है, जापान में एक न्यूक्लियर रिएक्टर का, दैट वाज नॉट ड्यू टू द एनी फॉल्ट ऑफ द न्यूक्लियर रिएक्टर, इट वाज एक्चुअली ड्यू टू द सुनामी. द सुनामी केम एंड द बिल्डिंग हैज कोलैप्स्ड, एंड दैट इज व्हाई द थिंग्स हैव स्प्रेड इन द सराउंडिंग्स. तो वो एक हुआ था एक 1989 में शायद, आई एग्जैक्टली डोंट रिमेंबर, 89 में चेरनोबिल. चेरनोबिल भी आपने सुना ही होगा, दैट वाज इन रशिया, and that was blasted. That was actually the error which has been done in the nuclear reactor, and that has blasted. So that also spread so many radioactive sample in the atmosphere, surrounding environment, everything. So 2 examples are there which is very they have a drastic impact. अगर उसको सही से रन नहीं किया ना, तो it has a very drastic impact. So that is why it is not fully converted to these kind of thing. तो अभी भी हम उस पे अच्छी, मतलब 10 years बहुत अच्छा काम चला. आफ्टर 45 अप टू 55 द थिंग्स वर डन इन अ वेरी मैनर. उसके बाद थोड़ा सा कम हो गया सारा काम, ये हार्मफुल है और प्रॉब्लम कर सकता है. सो दैट इज व्हाई दिस बिकम वेरी लेस मींस इन यूज. बट कंट्रोल्ड रेडियो एक्टिविटी, कंट्रोल्ड न्यूक्लियर रिएक्शंस आज भी हो रहे हैं आपके. एक सेकंड बेटा, एक सेकंड वेट करना, किसी का कॉल आ रहा है, जस्ट अ सेकंड. Okay, so when the nuclear reactor begin to form, what they have done, they have took the sample, means they took there is experimental setup, and that was a very small tank. That is not a big tank. It is around 7 centimeter, right? Exactly, means I will give you the number how much this centimeter is. 7 centimeter and something, which is very small. It is like a box type of cylinder. In that cylinder, what they have filled, with the heavy water and CdCl2, and they pointed their this cylinder, which is a kind of detector. They pointed this towards a source of neutrino. So there was a nuclear reactor from which the neutrino is coming out. So there was a source of new anti-neutrino. So there was a nuclear reactor. Near to that, they have kept this particular tank. Not very close. Obviously, उसके अंदर नहीं बैठ गए थे nuclear reactor में. It is very far because neutrino will come out from the nuclear reactor. There is no entrance. अगर आपने lead की line भी बहुत मोटी लगा रखी है, cement की है, फिर concrete की है, मतलब concrete है, cement है, then you have bricks and many things they put to have no harmful radiation should pass through these things. So, but still the neutrino can come out from the nuclear reactor. That was very easy for them. And this sample is filled with, this box is filled with these things. Why this one? Because this is a source of proton. So there are so many protons. H2O है, तो उसमें around आपके per molecule पे आपके पास अगर deuterium है तब भी still you have a 10 protons within one molecule. And if you have a good, if you take at least tons of water, then it is very good amount of proton you have. So there is a possibility that these neutrino, when they get into this tank, they can interact with the proton. These are neutrinos, antineutrino which is coming, and there is a proton, and they can hit the proton. And when they hit the proton, the reaction could happen. We have to wait because the reaction cross section is very less. Then this proton will produce a neutron and a positron. When this reaction happens, it will produce a neutron and a positron. अब ये पूरा हमारा जो मटेरियल फील्ड है ये एटम से फील्ड है. हमने कोई प्रोटॉन नहीं डाला हुआ, एटम्स डाले हुए. एटम के अंदर प्रोटॉन्स है और एटम्स में इलेक्ट्रॉन भी हैं. इलेक्ट्रॉन तो और ज्यादा है, कोई दिक्कत ही नहीं है. CDCl में भी है, उसमें भी जितने प्रोटॉन है ये हैव इलेक्ट्रॉन आल्सो. So this positron could not be a free particle. If the positron generated, it will easily find an electron and it will annihilate. तो जैसे ही positron emit होगा इस reaction के बाद, तो it will, what will happen? It will find an electron and it will do a annihilation and it will produce a gamma photon. These gammas will have 0.5 because they individually have 0.5 mega electron volt energy. So when they combine, they can produce two different gamma with 0.5 mega electron volt energy. तो दो photons emit होंगे और reason भी है एक photon emit नहीं होता है. We have two photons that we will do when we will do the interaction of radiation with matter. उसमें हम ये करेंगे कि why we have this reaction, that is positron plus electron is not equal to gamma. It is actually positron plus electron is 2 gamma. This is not a possible reaction. So we will see that also. Why there is only possibility of 2 gamma. हो सकता है 1 means इनको add कर दो तो 1 mega electron volt का एक gamma radiation form हो सकता था. There is no harm क्योंकि gamma radiation 10 mega electron volt तक के भी होते हैं. तो why this is not possible? We always have 2 gamma. So they will emit in opposite direction. Okay, so this is a possibility, first possibility. And the neutron which was generated by this reaction, that will not interact with any other particle easily, but it will, because when it is generated, because these are very high energy particle, so proton was stationary, so the momentum has to be transferred. तो momentum means proton तो stationary था, बहुत ज़्यादा motion नहीं था इसके respect में. तो जो neutron है, that will be a moving particle, very high velocity. Means at this, just when they are produced, they have a good amount of velocity. Means they are not very static. They will have certain motion. So what happens? They move in a erratic path. इधर उधर घूमते हैं, and when it go on hitting the other atoms, it slow down. Its energy get slow down. When its energy gets slow down, there is a cadmium nucleus, which is a good, having a good capturing power of neutron. Cadmium use होता है ना control rod के form में, boron and cadmium, if you remember. Boron और cadmium
Yes, sir.
use होते हैं ना nuclear reactor में. Why they are used? Because they capture the neutron. They are deficient of neutron actually. Their nucleus is deficient of neutron. So they easily capture the neutron, but they capture only slow moving neutron. Means those neutron which are normally called as thermal neutrons. Thermal neutrons means their kinetic energy is roughly equal to the thermal energy. Very, very feasible. So it means if you have a motion, if you have certain kinetic energy of neutron, then they don't get captured, but they form certain other reaction. तो हमें ऐसा एम रखना है कि इसको स्लो डाउन करना है, और स्लो डाउन होने से धीरे धीरे वो इतना स्लो हो गया कि वो थर्मल एनर्जी के आसपास पहुंच गया. एंड वंस इट इज सो स्लो दैट cadmium nucleus, this is a cadmium nucleus, they capture this. And when the cadmium nucleus means CD, actually जो यहाँ पे ना CD13 है, 113 है, when they capture a neutron they form CD114, and that is in excited state, that is not in a ground state. Whenever the neutron is get captured by these CD113, they go to the excited state. That is, CD114 will go to excited state, means it has to relax back. Whenever your nucleus is in excited state, it has to relax back to the ground state by emitting another gamma, which is roughly around 9 mega electron volt. So everything is happening within this tank, and out of the tank 3 things are coming. अगर ये तीनों आपके डिटेक्ट हो जाते हैं, if you are able to measure 3 photons of these energies, then you can say that one antineutrino has been captured by the proton. So this is a signal. So there was a scintillator detector they have kept. अब scintillator detector क्या है वो हम अक्टूबर में पढ़ेंगे, when we will do the detection of radiation. जो detectors है ना different तो उसमें पढ़ेंगे. तो there is a scintillator detector which is kept just above and below the tank, and they are called, means they are actually capturing the photons. उनका एम होता है कि अगर कहीं फोटोन है तो उसको कैप्चर करना और उसके रिस्पेक्ट में एक सिग्नल देना. तो what they have done, they have kept 2 scintillator detector up, one is up and one is down, and whenever they get these 3 photons measured, they say कि there is one capture of antineutrino was done by the proton. So this was the prediction. This was the theoretical analysis कि भाई ऐसा ऐसा होना चाहिए, and if you get the result, then you are confirming कि आपने एक antineutrino capture कर लिया. Okay, one more thing is that whenever the positron is generated, it quickly, very fast, get annihilated by the electron, and these 2 photons comes just after the reaction. And once this antineutrino combines with the proton, you get these 2 signals. तो ये सिग्नल आने ही आने, इनके में टाइम नहीं लगता है, because positron does not wait, it just annihilate with the electron. So these 2 signal is just after the capturing of antineutrino by the proton. But the neutron which is being generated, they travel for a certain distance, and once they become a very slow down, when they become a thermal neutron, then they are getting captured by the cadmium nucleus. So that take around 10 microseconds. तो इस न्यूट्रॉन को कैप्चर होने में इतना टाइम लगता है roughly. You can do the calculation also कि how much time will be there if a neutron is having this much of kinetic energy and hitting a nucleus regularly after certain interval. So how much time it will take to slow down to a thermal neutron? So it takes around 10 microseconds. It means when you get these 2 signal, and after 10 microseconds, if you get this signal, then you are 101% sure that antineutrino has been captured by the proton. तो ये दोनों सिग्नल और 10 माइक्रोसेकंड के बाद ये वाला सिग्नल. हो सकता है किसी रिएक्शन के बाद सिर्फ ये दोनों सिग्नल मिले, आपको ये सिग्नल मिले ही ना, तो दैट इज नॉट एंटीन्यूट्रिनो कैप्चरिंग बाय द प्रोटॉन, इट इज समथिंग एल्स. बट इफ यू गेट this kind of a characteristic result, means 2 signals of this much of energy, and after 10 microsecond again of gamma photon which is of this much of energy, then the reaction has happened. So they have waited for 3-4 years, they have done this experiment, and they got at least 2 to 3 events per hour, which was very small value. 2 to 3 events per hour. एक घंटे में हार्डली 1 या 2 न्यूट्रिनो ही कैप्चर हो पाते थे उनके सैंपल्स में. एंड दैट टाइम द थिंग्स वेर वेरी क्रूड. ये बहुत अच्छा इंस्ट्रूमेंट है भी नहीं न्यूट्रॉन को कैप्चर करने के लिए, एंटी न्यूट्रिनो को कैप्चर करने के लिए. दिस इज वेरी बेसिक इंस्ट्रूमेंट. यू हैव अ हेवी वाटर, You can even improve this system. तो आज के टाइम जो सिस्टम यूज होते हैं न्यूट्रिनो या एंटी न्यूट्रिनो को कैप्चर करने के, दे डोंट यूज हेवी वाटर, they use germanium crystals, or sometime you can see the very big tank filled with germanium only, pure germanium, and pure germanium is very difficult to get. So nowadays, और जो बैंगलोर में बन रहा है ना, शायद बैंगलोर और कर्नाटक में कहीं, वो जर्मेनियम बेस्ड ही है सिस्टम which is being formed for a capturing of these neutrino. Okay, so this is the reaction, the steps I have discussed with you, but in notes I have written in a order way कि पहले क्या होगा, दूसरा क्या होगा, तीसरा क्या होगा, that I will provide. ठीक है, so this is clear to you how the things has been done, and it took around 25 years. So 25 years लग गए जब इसका prediction हुआ न्यूट्रिनो का और उसके डिटेक्शन में. It took around 25 years, very large amount of time. 10 years तो पता ही नहीं चला करना क्या है. उसके बाद न्यूक्लियर रिएक्टर्स बने, then there is a source of anti neutrino you have got, then you can do the experiment. जब तक आपके पास सोर्स नहीं है तब तक एक्सपेरिमेंट कर भी नहीं सकते, because you cannot produce easily these things in a lab. But to justify that what we have written the experiment, what we have written the equations, inverse beta decay. So inverse beta decay में क्या था, this is getting captured by this one and this is getting captured by this one, and not the inverse is true, means this cannot captured by this one and this cannot be captured by this one. This is what the says. Mean you cannot see an anti-neutrino getting captured by a neutron or neutrino getting captured by a proton. So what they have done to justify this experiment also, ऐसा नहीं कि ये ऐसे ही कह दिया, इसको experiment भी किया. It was done by Davis and their co-worker. That is, they have done this experiment: anti-neutrino plus Cl37. It has proton also and neutron also. इसके अंदर दोनों है, proton neutron इसके अंदर दोनों है. But what they are trying to look a reaction in which if you have a electron and Ar 37, कैल्शियम का Z क्या है, सॉरी क्लोरीन का Z क्या है, कैल्शियम नहीं, क्लोरीन का Z क्या है, Z की वैल्यू, क्लोरीन के लिए Z की वैल्यू क्या है, Z क्या होता है क्लोरीन का, इसका तो 18 होता है आर्गन का, क्लोरीन का क्या होता है 17. So what is being changed? One proton has increased. इस रिएक्शन में क्या है, यहाँ पे 17 है, अब वो 18 हो गया, तो P में एक ऐड हो गया यहाँ पे, और N must be subtracted because you are getting 37. A की वैल्यू सेम है ना, तो एक प्रोटॉन कन्वर्जन हुआ है, न्यूट्रॉन एक डिक्रीज हुआ है, मींस इस रिएक्शन का मीनिंग है दिस प्लस अ न्यूट्रॉन giving me a proton plus an electron. This is a reaction which is not possible, as we have seen earlier. This is not possible. Anti-neutrino can only be captured by proton. This is possible, but this cannot be captured by a neutron. This is not possible. So people have done this experiment also, and the result is 0. They didn't find any reaction which is happening. This is actually radioactive argon. So they did not find a single radioactive argon. They have waited for around 5 to 6 or 10 years, but they have not got a single result where this kind of argon has been generated, and that is a radioactive argon. So this also has been done, whose result is 0, but they said कि yes हमने किया है, 10 साल तक एक्सपेरिमेंट किया है, and we have not got result, means this is not possible. ऐसे हम देखेंगे ये दोनों के क्यों ऐसी कंडीशन है. There is a conservation law which they have to follow, and this follow and this does not follow. पता है वो कंजर्वेशन लॉ का नाम क्या है, जो ये फॉलो कर रहे हैं ये फॉलो नहीं कर रहा है. एनर्जी कंजर्वेशन यू नो, लीनियर मोमेंटम यू नो, एंगुलर मोमेंटम यू नो. एंगुलर मोमेंटम के दो पार्ट हैं, ऑर्बिटल एंड स्पिन यू नो ऑलरेडी, पैरिटी यू नो. There is another conservation law which is being followed in this case and which is not being followed in this case. Anybody know what that conservation law is called? Have you seen this number somewhere in the book? Or have you heard?
Sir,
Lepton. Huh? Lepton.
yes, sir.
Lepton, actually these conservation law comes in the particle physics. Atomic physics या nuclear physics में थोड़ा सा ये उतना useful नहीं है, because nuclear physics जब तक हम deal कर रहे हैं, our aim is to not to change the number of proton and neutron. They should remain same before the reaction and after the reaction. हम कोशिश करते हैं कि वो करीब करीब सेम ही रहे, बहुत ज्यादा उसमें वेरिएशन हो. लेकिन जब आप पार्टिकल फिजिक्स करते हो, then you have these numbers, lepton number, baryon number, isospin number, all these things come into the picture. Some few more, strangeness number, charm number, bottom number, top number, all these numbers comes into the picture and all have to satisfy for certain reaction. So lepton is one of the basic things. तो lepton number कंजर्व होना चाहिए. ऊपर के केस में lepton number कंजर्व हो रहा है, नीचे के केस में lepton number कंजर्व नहीं हो रहा है. Okay, so here we finish off this particular topic, that is neutrino physics. एग्जाम में 10 नंबर के आसपास या हो सकता है 5 नंबर में. What are neutrino and give some of its characteristics and how they are detected. So you can write these things, which is not a very big thing. एक पेज का है, उससे ज्यादा नहीं है. Now we come to the gamma decay, which is the last decay.
Hello, sir.
हाँ बताओ.
Sir, first we said like to capture neutrino, we have to wait like 20-30 years.
Yes. If you're
But in the second experiment, you said that there was 1-2 detections per hour.
yes, that is means if you okay, let me give you one more number, then you can understand why this is so feeble. The source of neutrino was your nuclear reactor, from where they are getting the source, and that the flux of that source is something which is 10 to the power of 13 per centimeter square and per second. Yes. How many neutrino they are getting? This is the number of neutrino per centimeter they are getting. This is a very big number. Out of means every second you are encountering this much of every second. So in 1 hour, how many neutrinos have been passed through this sample, this particular tank? It is very huge number. You just multiply with 3600 and then you multiply with means at least you will multiply with 3600. There are 3 orders. So roughly it is 3.6 into 10 to the power of 16 neutrino you are getting per centimeter square in 1 hour. Out of that, you are getting 1 or 2 getting captured per hour. That is, if you compare these two numbers, it is not so equivalent. If you are getting this much of number, out of that only 1 or 2, so the probability is very small. It is -16. मतलब 1-2 neutrino in 1 hour. If I say I give you only 4 neutrino per hour, then you can say that is a good amount. कि 1 या 2 को मैं capture कर पा रहा हूँ. If you are giving me 4, but I am giving you 10 to the power of 16 neutrino per hour, and you are getting capturing only 1 or 2. So that is very feeble kind of probability of getting a reaction of this neutrinos. ये number मैंने उस समय नहीं दिया, उस समय मिस कर गया. Either what is the flux value? Flux value is very high. So in comparison to that, 1 or 2 neutrino is very small number. That is hardly detectable number. ठीक है.
Yes, sir.
और अगर मेरा सैंपल, अगर मैंने ये टैंक ही मैंने 110 लाइट ईयर का बना देता हूँ, तो what I will get, this much number of reactions I will get, or this much of number of reactions. All the neutrino has to get captured by this particular tank. So you will get that kind of thing. Means अगर आपका टैंक बहुत बड़ा है, तो सारा का सारा न्यूट्रिनो आपका सबके सब कैप्चर होने ही है. Everyone will give me a signal. So you will say कि in hour I am able to capture this much of neutrino. If your tank is very big, if your tank is small, you have to wait to catch all the neutrino, or you have to you will get only feeble amount of neutrino which is getting captured. Or there is a reason also. There is one more thing that we don't go into detail, but those neutrinos, because the shower of neutrino have different energy also, means all the neutrinos which are coming from the this nuclear reactor source, they don't have the same energy. They have energy distribution also. So every neutrino does not have the same value of energy when they are coming out from the nuclear reactor. So that energy is also having a variation, and only those I have the number, I think they have written the number. Only those neutrinos which have certain amount of energy, only those are getting captured, and rest of them have lesser energy, they get just pass. So that number I have not written somewhere, but there is a number also, that if the neutrino is having this much of energy, then only they are getting detected, otherwise they just pass. So that is also there. I will write that number in the notes also, ki how much that energy should be there for the neutrino. So there is a distribution of energy for a neutrino which is coming out from the nuclear reactor. So only those neutrino having this much of energy, they will capture, and out of that also very few are getting captured, even though the number is very good. The incoming flux is very good amount. Okay. You can compare that with the fission of a uranium-235. Every uranium-235 emits a 3 proton and 3 neutron, and those 3 neutron are capable of generating further more. I mean, they are capable of getting means they are going to do a reaction with the uranium-235, and they again produce a 3 more. So that is why every neutron which is generated, they have a capability of reaction. So there you can say 3 are generated and 3 have a possibility of reaction. Here you have 10 to the power 16 generated, hardly 1 or 2 are getting reacted. So this is how you can compare why they are so feeble and why we have to wait for some time, or we have to make the detector so long so that we can measure or we can detect all the neutrino. Okay, so let us. Is it clear to you, or still you need explanation?
No, sir,
Yes.
it's clear.
The reaction which is being 1 or 2 per hour is very small number in comparison to the flux. The flux value is very high. Okay, so let us go to the last topic of the radioactivity, that is your gamma decay. Gamma decay is not that much lengthy, because we will do the energetics of gamma decay. We have an internal conversion and angular momentum and parity selection rule. बस इतना ही है, इससे ज्यादा नहीं है. हाँ, फिर खत्म हो गया, फिर हम न्यूक्लियर रिएक्शंस पर शिफ्ट हो जाएंगे. ओके, सो ओके, गामा डीके, और कई बार कहते हैं गैमा डीके, इट इज मोर प्रोनाउंस्ड एज गैमा, क्योंकि इंडिया में गामा पहलवान एक हुआ करते थे, ही वाज सो स्ट्रेंथफुल. याद किसी को पता है कि गामा पहलवान भी कोई था? किसी को पता है ये कहानी? ये ऐसा तो नहीं लग रहा कि मजाक ही कह रहा हूँ मैं, हाँ? गामा पहलवान किसी का नाम रखा गया था. He was very strong. Gamma phelan. Gamma is very strong radiation. They are very. It just causes cancer. If you get means what you can say. If you get somehow, if you are exposed to these gamma radiation, definitely your DNA is going to change, because they are very strong photons. Their energy is very high. Normally, every time the Earth have this radiation, the sun is emitting this radiation, and when it is emitting a radiation, gamma is also there. Even particles are there. Gamma is actually photon, it is not a particle. अल्फा बीटा पार्टिकल्स थे और गामा हमारा प्योर रेडिएशन है, दैट इज इलेक्ट्रोमैग्नेटिक रेडिएशन. अल्फा एंड बीटा वेर नॉट इलेक्ट्रोमैग्नेटिक रेडिएशन, दे वर पार्टिकल्स. So gamma is exactly a electromagnetic radiation and they're very strong. Their wavelength is very small, 10 to the power of minus 18, minus 15, minus 20, something like that, very strong. The energy range is, if you talk about the energy range, what is the value of energy of these photons, which is 0.1 mega electron volt to roughly 10 mega electron, very strong. X-ray का क्या है? एक्सरे का हमने लास्ट टाइम देखा था अराउंड 100 ऑफ किलो इलेक्ट्रॉन वोल्ट या उससे भी फ्रैक्शन में है 80 50 समथिंग लाइक दैट. इट इज अगेन वन ऑर्डर मोर देन दैट and that go up to 10 mega electron volt, very strong. So the energy is very high and mostly what happens whenever your sample is there, if you have a beta decay or a alpha decay, we have seen earlier that there is no restriction that the ground state parent will decay into the ground state of daughter. There is a possibility that ground state parent could decay into any excited state of daughter because parity has to be followed, angular momentum has to be followed, and sometime what happens कि daughter का ground और parent का ground दोनों की parity और angular momentum match नहीं कर रहे, तो that alpha and beta decay could not be possible. So it will decay into some excited state. तो उस एटम उसी पर्टिकुलर न्यूक्लियाई का कुछ एक्साइटेड स्टेट होगा जिसमें पैरिटी और आपके नंबर मैच हो रहे हैं. तो इफ इट इज मैचिंग, सो देयर इज अ पॉसिबिलिटी दैट, और इट इज नॉट अ पॉसिबिलिटी, इट इज 100% टाइम व्हाट हैपेंस दैट whenever the alpha and beta decay happens, the nuclei which is left over, that is a dot nuclei, it is always in an excited state, and these excited state nuclei will get back to the ground state by emitting a gamma. तो गामा जो डीके है ना वो एक्साइटेड स्टेट से रिलेटेड है न्यूक्लियस के. वो न्यूक्लियस की अनस्टेबिलिटी को डायरेक्टली नहीं देख रहा है, मींस नंबर ऑफ प्रोटॉन नंबर ऑफ न्यूट्रॉन की अनस्टेबिलिटी का रीजन नहीं है यहाँ पे, व्हिच वाज रीजन फॉर द अल्फा एंड बीटा डीके, बट हियर द डीके इज ड्यू टू द एक्साइटेड स्टेट इज गेटिंग बैक टू द ग्राउंड स्टेट. और जो एनर्जी स्टेट्स हैं न्यूक्लियस के, दे आर इन मेगा इलेक्ट्रॉन वोल्ट, दैट इज व्हाई दिस एनर्जी इज मेगा इलेक्ट्रॉन वोल्ट. So why, if someone asks why the gamma photon are of the range of mega electron, why don't we have a kilo electron volt range? So you can easily say, okay, sir, the state in the nuclear means within the nucleus, the proton in a different orbits are there for the proton and different orbits are there for the neutron, and these orbits have their energy difference in mega electron volt. किसी का 0.5 होगा, 1 हो सकता है, 1.5 हो सकता है, 0.7 हो सकता है, 0.2 हो सकता है, but they all in the range of mega electron volt. So any transition when is happening, means any proton or neutron when it is jumping from higher state to lower state, it will emit a photon of a mega electron volt range only. So if it that kind of range, then it is a gamma photon. So the reaction is very simple. If you write a gamma, so normally what happens, we write, इसमें a z और x नहीं भी लिखोगे ना, it is okay. What you have to write? You have to write that is an excited state and that goes back to a ground state and by emitting a gamma photon. This is the reaction. यहाँ पे कोई a n और z में कोई change नहीं है, they all are same thing because only the higher proton, higher energy orbit proton or neutron has jumped to the lower orbit. That is what is happening. Okay, so this is the only equation we have. Obviously, whenever the mass is more, when you have more mass, whenever you have any nuclei which is in excited state, its mass will be more. And with the nucleus in the ground state, its mass will be less. We have already seen this thing. Binding energy से कहीं ना कहीं relation है. तो जब भी excited state में जाओगे, you have to borrow the energy from the binding energy, and that will be dumped in the form of heaviness. So that is mass is increased. And whenever the binding energy increases, the mass has to decrease. So that is what is happening in the ground state. Ground state में binding energy ज़्यादा है और इसमें binding energy कम है. Mass ज़्यादा है, यहाँ पे mass कम है. This vice versa. Okay, so when first we do the energetics, if we go for the energetics, and we can write that before the reaction we have only EI. EI is the energy of the nucleus in the excited state. Energy of the nucleus in the excited state. And finally we have energy of the nucleus in the final, that is ground state. रिएक्शन से पहले यानी डीके से पहले हमारे पास सिर्फ ये एनर्जी है, डीके के बाद हमारे पास ये एनर्जी है, प्लस वी हैव सम एक्स्ट्रा एनर्जीज आल्सो, वी हैव ई गामा जो गामा लेके जा रहा है अपने साथ, एंड प्लस वी हैव टी आर. टी आर इज द रिकॉइल ऑफ द डॉटर न्यूक्लियाई. यहाँ पे डॉटर न्यूक्लियाई कहने का मीनिंग ही नहीं है क्योंकि डॉटर न्यूक्लियाई और पेरेंट न्यूक्लियाई सेम है, ओनली द लेफ्ट ओवर न्यूक्लियाई आफ्टर गेटिंग डी एक्साइटेड. जब वो डी एक्साइट हो गया तो उसका न्यूक्लियस का रिकॉइल, तो न्यूक्लियस इज whenever it is emitting a gamma it will have a recoil. Obviously when it is emitting a bullet it will have to recoil, the gun has to recoil. The same thing is going to happen here also. Okay, this is the energy conservation you can write for this particular reaction. Then the momentum conservation.
Not visible.
हाँ बताओ.
So your screen is not visible, like screen share नहीं हो रहा.
मैंने शेयर किया था, एक मिनट रुको दोबारा मैं करता हूँ. I have shared I think. Okay. Okay. तो मैंने ऐसे ही लिया ये.
Now it's showing, sir.
Okay, so this is gamma decay. The energy I have written here. The reaction is this one. This star is denoting an excited state nucleus. This no star means ground state and gamma is being emitted. This is the energy conservation before the reaction or before the decay process. Only EI was there, which is energy of this nucleus. After that, the energy of the nucleus plus the energy of the gamma and plus the recoil of the nucleus. This is what the three component you have in the energy. And when we talk about the momentum, before the reaction, before the decay, let us understand that the nucleus was in rest. So the 0. And after the emission of gamma, the total means PR, recoil momentum of the nucleus plus the gamma. Both must add to 0. Means obviously there, if you make a direction, that will be something like this one. They must be equal, PR gamma and P gamma. In magnitude, they must be equal and opposite. It is something like that. So that has to be 0 because before the emission of gamma, and the nucleus was in rest. So that should be 0. Okay, photon have momentum. Photon के पास momentum होता है? Do the photons have momentum? होता है नहीं होता है? I'm asking actually. I'm not saying you कि उनके पास momentum होता है. I'm asking you. अगर लिखा है तो शायद होता ही होगा. Answer could be this one. सर आपने लिखा है तो होगा. होता है या नहीं होता है? होता है तो कितना होता है? If it is there, then how much that value is? बताओ कुछ हिंट दो. Do the photons have momentum? They are electromagnetic radiations. Radiation के पास क्या momentum होता है?
Yes, sir.
हाँ?
But Compton effect.
कॉम्पटन इफेक्ट में, अच्छा कॉम्पटन इफेक्ट में आपने कंजर्वेशन ऑफ एनर्जी भी किया है, कंजर्वेशन ऑफ मोमेंटम भी किया है.
हाँ सर.
हाँ, yes. Okay, relativistic energy equation for photon would be this one. Since photon have zero rest mass, it means here energy is equal to Pc. It means momentum is E upon C. That is h nu by C. So this must be the momentum of every photon. अगर उसकी एनर्जी गिवन है तो उसको C से डिवाइड करो and that is your momentum. Means photon और radiation carries momentum. Radiation के सिर्फ एनर्जी नहीं होता, they also have momentum. तो उनके पास लीनियर मोमेंटम है, और लीनियर मोमेंटम है तो बाद में एंगुलर मोमेंटम भी हो सकता है. तो लीनियर मोमेंटम तो थोड़ा सा हम अवॉइड करते हैं, बट रेडिएशंस हैव एंगुलर मोमेंटम एंड दे हैव गुड अमाउंट ऑफ एंगुलर मोमेंटम. ऐसा नहीं कि नहीं होता. They have a capability of rotating any object. If you go on hitting a photon to any particular very light object, the light object will start rotating because they have momentum, they have angular momentum. तो कभी ऐसा एक्सपेरिमेंट अगर करने को मिला या डिजाइन कर सकते हो, तो you can design an experiment in which if you bombard a photon, means light is being bombarded on a certain very light particle. Obviously, the light has to be monochromatic or very phase coherent kind of light. Then what will you see that when it is hitting something, any object which is very light, it will start rotating. So that is they are having angular momentum. They can have a rotational effect. Okay, so this is the momentum value. P is E upon C. So this is how you equate the equation, because rest mass is 0. So this goes off. We're left with only these two numbers. Okay, so EI minus EF can be written as E gamma plus TR. And this can be written as delta E, with the energy difference between excited state and ground state. This is delta E. Energy difference between excited and ground state. E gamma plus TR can be written as PR square upon 2m, mass of nucleus. E gamma plus this PR can be replaced by P gamma square upon 2m. What you can do, you can multiply C square and divide by C square. So E gamma plus this number is E gamma square divided by 2m C square. वैसे तो इक्वेशन हम यहीं पे खत्म कर सकते हैं, कोई दिक्कत ही नहीं है, because if you look at this equation, this is very small. E gamma की वैल्यू आपकी होगी, let us say in mega electron volt. इसका स्क्वायर भी कर दोगे, अगर 10 भी है तो उसका 100 का हो जाएगा. This value, a nucleus rest mass energy, which is very high. एक प्रोटॉन का ही कितना होता है? 1 गीगा इलेक्ट्रॉन वोल्ट आता है, सिंगल प्रोटॉन. तो अगर आपके पास कोई न्यूक्लियस, हेवी न्यूक्लियस है जिसमें ए की वैल्यू 10 भी है, 20 भी है, 30 भी है, 40 है, तो इट इज ऑलवेज मोर देन दिस वैल्यू, very large value. So when you compare these two, so that is hardly any number. So that is very small. You can neglect it. अगर हम यहाँ neglect नहीं भी करते हैं तो let us write in the quadratic form. So E gamma square can be written as 2m. So let me write in a quadratic form only. सारा हम एक ही साइड लिखते हैं, इक्वालिटी को हटा देते हैं. E gamma square, this is this term, plus 2mc square E gamma minus 2mc square delta E, and that is equal to 0. So this equation, just multiply this number with E gamma and this number with delta E, and that is here. E gamma square ये रहा, E gamma वाला टर्म ये रहा, और ये आपका कांस्टेंट वाला टर्म है. तो दिस इज समथिंग लाइक a square x plus b plus c equal to 0. The quadratic equation. So, and quadratic of E gamma. So E gamma, its root will be minus b, that is 2m c square plus minus root of b square that is 4m square c4 minus is already there, so plus 2, there's nothing here, a is 1, so that is 4mc square delta E square, sorry m4 and c square, ए स्क्वायर था ना, तो ये 4 हो जाएगा, m स्क्वायर हो गया 4ac. Okay, no, let me just write it again. This will be 4ac है ना, इसको स्क्वायर में कौन कर रहा हूँ, प्लस 4ac means 4 into 2, that is 8, a is 1, c is this one, so that is mc square delta E. Okay, this one is there, and divided by 2a, so divided by 2 only because a is 1. ठीक है, एक बार देख लो करेक्शन, कहीं अगर कुछ मिस हुआ है तो जस्ट टेल मी, कोई नंबर अगर मिस हुआ है तो. So this can be written as minus mc square because 2 is there, ये 2 इसके अंदर भी जा सकता है, तो 2 4 जाएगा, तो 4 ये 4 कैंसिल हो गया, यहाँ 2 बचेगा, तो लेट मी राइट इन दैट फॉर्म, रूट ऑफ m square c4 plus 2 mc square delta E. And you can further, what you can do, you just take प्लस वाला हम लेते हैं, माइनस वाला नहीं लेते हैं. माइनस वाला इसलिए अवॉइड करेंगे because we cannot have a negative value for the photons, so we can assume that this is plus. You can even write plus minus also, there is no harm in that, and finally you can write that equation, but we will take it as plus. And what we will do the binomial expansion of this term. या तो इससे पहले हम इसको भी कॉमन ले लेते हैं, mc स्क्वायर को कॉमन ले लेते हैं, तो हमारे पास इक्वेशन क्या बच गया, 1 plus 2 delta E divided by mc square to the power of half. तो इस टर्म का हमें बायनोमियल एक्सपेंशन करना है. Just do the binomial expansion, and up to 3 terms you just write. How? What are those terms? A plus x to the power of half. This is what you have to expand. तो एक पहला टर्म 1 आएगा, दूसरा कोई एक टर्म आएगा जिसमें 1/2 का टर्म होगा, फिर 1/4 का टर्म होगा, and maybe something like this, maybe 1/1 factorial, 1/2 factorial, 1/3, and so on. Just give me all the first 3 terms only, because as you go for furthermore, the delta E by mc square is very small number, so that is going to reduce, वो एक नेग्लिजिबल वैल्यू हो जाएगी. तो डेल्टा ई आपका मेगा इलेक्ट्रॉन वोल्ट में है और mc स्क्वायर आपका गीगा में है, सेवरल गीगा है. That number is very small as you go on squaring that number or having a higher power. तो एक बार जरा फर्स्ट टर्म तो 1 होगा, that I will write. It is very easy. नेक्स्ट टर्म क्या होगा, x/2 होगा, 1 plus x to the power of half.
Delta E by mc square.
2 delta E by mc square, so divided by 2, that will be delta E by
mc square.
mc square. What about third term, plus or minus? It will be minus because n into n minus 1 होगा ना, n हमारा half है, into half minus half, that will be minus half. 1/4 का टर्म आ जाए तो माइनस आएगा, और बाकी उसके टर्म्स क्या होंगे,
Sir, 1/4 delta E by mc square whole square.
1/4 और 1/2?
1/4 sir.
ध्यान से चेक करो,
Sir, it's like 1 by 8 x square. So,
And 2 factorial भी तो आएगा.
हाँ sir, including 2 factorial.
Must be 1 by 2. चेक करो एक बार. 1 by 2 होगा या 1 by 4 होगा?
Sir, 1 by 4 होगा ना?
देखो ये हमारे पास कितना आ गया, n into n minus 1 that is half
1
into
by
half
4
that is 1 by 4
by 2
तो मेरा ये
factorial.
नंबर आ गया divided by 2 factorial so that is 2 so 1 by 8 तो आ गया हमारे पास और
Into 2.
पहले से हमारा इसका 2 है ना तो इसका
Yes.
स्क्वायर भी तो होगा that is 4 1 by 2
हाँ right sir, वो 2 का स्क्वायर करना होगा.
4 into delta E square upon m square C4 so that is 1 by 2 and we have further more term which is cube and we will neglect those values because this is very small number. So if we restrict ourselves, means if we restrict to 3 terms only, then this is mc square, you multiply with this one that is delta E, multiply with this one that is minus 1 by 2 delta E square divided by mc2 mc square क्योंकि यहाँ पे mc square है ना तो ये तो कैंसिल हो गए यहाँ पे वो डबल पावर में तो that is half. So this will be something which is delta E minus half delta E square and mc square, which is roughly equal to delta E. Okay, because delta E is much smaller than mc square, so we can neglect this one. Even we do the binomial expansion and all the quadratic solution, then also it is delta E. Or initially we can say that it is roughly equal to delta E. So this is the energy which is being carried by the gamma. So gamma will have energy roughly which is equal to delta E. That is the energy difference between excited state and ground state. तो गामा कितने का एमिट हुआ, गामा कितने मेगा इलेक्ट्रॉन वोल्ट का है, that is nothing but the energy difference between excited and ground state. Okay, so why these radiations are coming from the nucleus? Even though there is a transition of protons are happening, and why the radiation is emitting out? Why don't we have any other things? Do there is any source of radiation in the nucleus? Is there any source we have in the that is going to produce a radiation? हमारे पास सोर्स है अंदर न्यूक्लियस के अंदर सोर्स है हमारे पास जो रेडिएशन जनरेट कर सकते हैं. रेडिएशंस कहाँ से जनरेट होते हैं? हाउ द रेडिएशंस आर जनरेटेड? व्हाट इज द सोर्स ऑफ रेडिएशन?
Sir, can you repeat the question?
Why do we have radiation which is being emitted, that is electromagnetic radiation, when we have a transition of electron and protons? Sorry, not electron, neutron and protons. So I'm asking that do we have a source of radiation within the nucleus? हमारे पास जो न्यूक्लियस है, does it has a capability of generating a radiations? And what are the different kind of radiation it can generate? Electromagnetic is one thing. In that, do we have any differentiation that this is a this kind of electromagnetic, this is a this kind of electromagnetic, this is a this kind of electromagnetic? अच्छा, radiation generate क्यों होते हैं? Why we get radiations? What is the source of radiation?
Sir, oscillating charge.
Yes, oscillating charges. In nucleus, we have oscillating charges. You have protons, Even in the neutrons, we have certain charge. So protons, they form a different kind of moments. They can form a dipole moment kind of picture. They can make a quadrupole moment kind of picture. They can make a single nuclei kind of, means single charge kind of picture, but that is not going to generate any radiation. So for a radiation, you should have a dipole kind of arrangement. You should have a quadrupole arrangement. You can have an octopole arrangement. And even you don't have only charge arrangement, but there is a current also, because all the things are moving. So there is a current also. So current can generate magnetic kind of character. तो आपके पास रेडिएशन जनरेट करने के सारे important ingredients हैं within the nucleus, and they all are moving. And when they are moving, they are forming certain, means whenever the nucleus in an excited state, its shape is not spherical. It is obviously deformed. That shape will be something like ellipsoid. Either it is in the plane of xy, or it is in a, along the z-axis. So that is something like ellipsoid. And that ellipsoid is vibrating very fast. And when it is vibrating, there is a time dependency of these moments. Means dipole is changing with respect to time, current is changing with respect to time, quadrupole moment is changing with respect to time. And whenever they have a time variation of these charges or current arrangement, you have a radiation. So actually the nucleus which is emitting a radiation is nothing but an electromagnetic radiation because of its deformation. And the deformation of the nucleus is more prominent when it is in an excited state. तो सारा जो हमने मोमेंट्स स्टार्टिंग में पढ़े थे ना, 4-5 मोमेंट्स, डाइपोल मोमेंट पढ़ा था, मोनोपोल देखा था हमने जो इलेक्ट्रिक चार्ज के लिए होता है, डाइपोल हमारा मैग्नेटिक होता है, फिर हमारे पास क्वाड्रपोल इलेक्ट्रिकल होता है, ऑक्टोपोल मैग्नेटिक होता है, एंड सो ऑन. So there is a different moments, and these moments changes with respect to time when you have excited state, and they are producing a radiation. Okay, so this is the source of radiation from the nucleus. There is a variation of these moments with respect to time. Okay, so before going into the angular momentum or parity selection rule, we will discuss quickly, because we have 20 minutes, we will discuss the internal conversion. What is internal conversion? So let me just have one more file, which must be the last file for today. And I have to share that also. So instead of producing a radiation, when the nucleus is deformed and when it is getting relaxed back to the ground state, sometime what happens, these moments, means these electromagnetic moments, they generate electrons. What they do, instead of emitting electromagnetic radiation, these moments interact with the atomic electrons and cause the atomic electron to be emitted. What happens? The different multiple moments of the nucleus, it interacts with the atomic electrons, and the atomic electrons get emitted from the atom. तो हमारे पास न्यूक्लियस है ये, and it is getting very, means deformed, and it has a certain kind of multiple expansion. So it can have electrical nature, or it can have magnetic nature of moment, or electrical nature of moment, or even combined form also. What it do, you have the atomic electrons. So this moment, whatever the electrical or magnetic moment, they interact with these electrons, atomic electrons, and cause them to get out from the atom. So instead of emitting a gamma photon, they emit electron also. यानी गामा डीके सिर्फ फोटोन का एमिशन नहीं है, गामा डीके इलेक्ट्रॉन का एमिशन भी है. तो gamma decay is related to actually the photons only, but not every time the photon is emitted, sometimes the electron is emitted, and that is also gamma decay. Means a nucleus could relax back from excited state to ground state by emitting an atomic electron, not an electron which is being generated within the nucleus. ये ध्यान रखना, बीटा डीके में भी इलेक्ट्रॉन एमिट होता था, but बीटा डीके का इलेक्ट्रॉन क्या था? They are getting generated in the nucleus. Neutron or proton, when they are getting decayed, a new either electron or positron, they are being generated. Those are not atomic electrons, and they are getting coming out from the atoms. So it will look like as if the beta decay is going on, but it is not beta decay. You have to identify these electrons, and their energy is unique. In beta decay, you remember the energy is continuous. तो अगर कोई कहता है कि आपने तो इलेक्ट्रॉन डिटेक्ट किया है और आप कह रहे हो कि गामा डीके हो रहा है, ऐसा कैसे पॉसिबल है? अभी तक हम पढ़ रहे थे कि इलेक्ट्रॉन जब भी हमें डिटेक्ट होगा when it is coming from the atom, so that we will call it as a beta decay. And now you are saying it is a gamma decay. How this is possible? This is possible only if the electron which you have measured, it has a unique energy. Beta decay में वो energy unique नहीं होती थी. If you measure 10, if you detect 10 electrons, all will have a different energy. But in electron, this is called an internal conversion. So in internal conversion, when the electron is emitted, and these electrons are atomic electrons, they are not generated anywhere. They are atomic electrons. They are already existing in the atom, and they are getting emitted. And why they are getting emitted? Because they are interacting with the field of nucleus, which is in electric in nature or could be magnetic in nature. So they are interacting with the field of the electromagnetic field of the nucleus. That is why they are getting emitted, and they have a unique energy. They have a unique energy. So this is a basic difference between a electron which is emitted, that is not always a beta decay. It could be a gamma decay. तो अभी तक हम gamma decay क्या पढ़ते थे? Photon emit हो रहा, photon emit हो रहा, photon emit. Now the electron which is emitting, that could be a gamma decay process, but उसको हम gamma decay precisely नहीं कहते हैं, उसे हम कहते हैं internal conversion. So that is called a internal conversion. The energy, बहुत calculation हम detail में नहीं जा रहे हैं. The energy which is being carried by these electrons, which are atomic electron, already existing electrons, they are getting emitted from the atomic orbit. That energy is roughly equal to delta E minus the binding energy of those electrons. Delta E क्या है? EI minus EF. Nucleus का excited state का energy minus ground state का energy. So that is your delta E. Minus this binding energy means wherever the electron is, आपने जिसको remove किया, 1s को किया, 2s को किया, 3s को किया, 4s को किया, 4f को किया, 3p को किया, whatever the electron you have emitted, whatever the electron has been emitted, binding energy of that electron with the nucleus, that is B, this one. And this is your, and this number will be unique. ये continuous नहीं हो सकता है, because यहाँ पे कोई third particle नहीं है. जैसे उसमें न्यूट्रिनो एमिट होते थे and energy is being shared between two particles. Here the total energy, whatever the energy you calculate, that is given to the kinetic energy of it. These electrons are of unique energy, and that is are coming due to gamma kind of process. But उसका process का नाम क्या है? Internal conversion. That is called as internal conversion. So this is called an internal conversion. Okay. So whenever if you have a sample जिसमें बीटा डीके भी हो रहा है, गामा डीके भी हो रहा है, तो सैंपल का अगर आप मेजर करते हो इलेक्ट्रॉन का स्पेक्ट्रम कि जो इलेक्ट्रॉन एमिट हो रहे हैं उनकी एनर्जी आप बैठ करके मेजर कर रहे हो. तो इफ यू ट्राई टू मेजर व्हाट यू विल एबल टू सी दैट इफ यू सी नंबर ऑफ यू विल से बीटा पार्टिकल, आपको लगेगा कि इलेक्ट्रॉन आ रहा है, यू डोंट नो व्हाट इज दैट इलेक्ट्रॉन इज, वो जनरेट हुआ था इलेक्ट्रॉन या वो इलेक्ट्रॉन आपके एटॉमिक इलेक्ट्रॉन्स है, यू डोंट एबल टू आइडेंटिफाई. बट व्हेन यू लुक एट दिस पिक्चर, जब आप स्पेक्ट्रम का पिक्चर देखते हो तब आपको क्लियर हो जाता है कि फ्रॉम वेयर दिस इलेक्ट्रॉन्स आर कमिंग, वो न्यूक्लियस में जनरेट होकर के बाहर आ रहे थे या एटॉमिक इलेक्ट्रॉन्स थे. तो व्हाट यू विल सी, दिस इज द बीटा डीके व्हिच वी हैव ऑलरेडी सीन. दे हैव अ कंटिन्यूस एनर्जी, उनकी एनर्जी यूनिफॉर्म होती है, मतलब जीरो से लेकर के आपके पास एक मैक्सिमम टी, जिसको टी मैक्सिमम कहते थे, वो एनर्जी तक दे हैव। कुछ ना कुछ आपको डिफरेंट डिफरेंट बीटा पार्टिकल मिलेंगे, डिफरेंट डिफरेंट इलेक्ट्रॉन्स यू विल फाइंड, दे हैव अ यूनिफॉर्म कंटिन्यूअस वेरिएशन ऑफ द एनर्जी. But if you find, means with this particular curve, if you have this kind of picture, just let me use different color. So there will be overlapping. आपके पास सारे इलेक्ट्रॉन तो मिल ही रहे हैं, कुछ इलेक्ट्रॉन ऐसे भी होंगे which will you will able to see like this. Their energy is this one. So this peaks suddenly which is appearing in the background of this beta decay, ये peaks जो emit हो रहे हैं आपके पास, these are electron converted, means these are due to internal conversion, means those electrons which are coming from the atomic orbits and they are getting out because of interaction with the electromagnetic multiple moments of the nucleus during the beta decay process. So this is one of the competing process with respect to गामा. तो गामा के साथ ये compete करता है. बहुत सारे केसेस में क्या होता है कि हमारे पास फोटोन एमिट होते हैं, लेकिन बहुत सारे न्यूक्लियस में हमारे पास इलेक्ट्रॉन एमिट होते हैं ड्यूरिंग द बीटा डीके, गामा डीके. तो गामा डीके हमेशा फोटोन से रिलेटेड नहीं है, इलेक्ट्रॉन से भी रिलेटेड है, बट दैट प्रोसेस इज कॉल्ड एज इंटरनल कन्वर्जन. प्योरली द एनर्जी वैल्यू इज रिलेटेड टू द गामा थिंग. तो गामा में जितनी एनर्जी रिलीज होनी है उतनी यहाँ पे भी होनी है, बट यहाँ पे इलेक्ट्रॉन एमिट होंगे, फोटोन नहीं एमिट होंगे. तो बहुत सारे एटम हैं जो फेवर करते हैं इंटरनल कन्वर्जन को इंस्टेड ऑफ गामा डीके को. सो दिस इज अ कंपीटिंग प्रोसेस विद द गामा डीके. बहुत सारे एटम्स में ये एग्जिस्ट करते हैं. लेट अस टेक एन एग्जांपल. फॉर एग्जांपल, अगर कैलकुलेशन कल को आ जाता है एग्जाम में, आज हमने डेरिवेशन ज्यादा नहीं किया है, बहुत स्मॉल स्मॉल फॉर्मूला ही लिखे. So let us have a reaction in which Hg is doing a beta decay and then converted into Tl. Thallium है, क्या है? Thallium कहते हैं इसको, Tl को. This is a beta decay. And this Tl, after a decay, it is in excited state, and that goes back to a ground state. And a gamma which is detected, that is 279.1, sorry, 9.90 kilo electron volt, 190. This is 190. Let me write it again. This gamma is 279.190 kilo electron volt. When you have this reaction, means this beta decay is there. After beta decay, there is a gamma photon which is emitted like this one. But not only gamma photon, sometimes the electrons are coming out. Because this has happened, it has a unique energy. यहाँ पे जो इलेक्ट्रॉन एमिट होगा उसका एक एनर्जी यूनिक होगा, या उसका एक कंटिन्यूस एनर्जी आएगा आपके पास कि मैक्सिमम एनर्जी, यानी इस केस के लिए T maximum you can easily calculate by the mass difference of these two, that you can perform easily, that may come in mega electron volt. But you are getting several other electrons of certain unique energy, and that is due to the internal conversion which is competing with the emission of gamma. तो gamma emission की जगह पे कुछ atoms ने internal conversion को favor किया. In that case, the electron is being emitted, and those electrons are atomic electrons. And their energy we can easily predict if we know the binding energy value of the thallium. अगर TL का binding energy हमें पता है, यानी sum of the few binding energy, K shell यानी 1s, K shell का binding energy की value है -85.529 kilo electron volt. Binding energy of L first, which is roughly -15.347 kilo electron volt. So what is the value of electron? What is the kinetic energy of the electron which is coming from K shell due to internal conversion? क्या value होगी उसकी? इक्वेशन आपके पास ऊपर है, this is the equation. So you have to calculate the TE. How much TE will be there means kinetic energy of the electron which is being emitted from the K shell. अगर K shell से कोई इलेक्ट्रॉन emit होता है तो उसकी एनर्जी क्या होगी, kinetic energy. If these two are the binding energy of K and L1, दो का मैंने लिख दिया है, बाकी और भी हैं that I'm not writing, I'm just giving you idea कि how you have to calculate. How much this energy will be? Delta E minus B. कितना होगा, कैलकुलेट करो. On the way, क्या हुआ, कहीं पहुंचे या रास्ते में है या कहाँ पे हैं? हमेशा पूछता हूँ मैं कि रास्ते में हो या नहीं हो, या बैठे हो बस. इस क्वेश्चन को करने के बाद फिर फ्री हो, फिर सिलेक्शन रूल नेक्स्ट टाइम करेंगे या ट्यूट क्लास में कर लेंगे हम. इसके बाद फ्री हो, थोड़ा सा टॉपिक रह गया है that we will discuss in the next class and we will start the nuclear reaction, but ये क्वेश्चन करके जाना है.
Sir, 380.
थोड़ा सा गड़बड़ किया आपने, वो गड़बड़ मैं बताऊंगा कहाँ पे किया है. It cannot be more than that value. The डेल्टा ई को क्रॉस नहीं कर सकता वैल्यू. एक बार फिर से देखो ध्यान से क्या गड़बड़ हुआ है. यू कैन नॉट क्रॉस डेल्टा ई.
Sir, like B will be a negative number, right? So won't it be over
Yes.
than delta?
Yes, everything is in the B. You know, the 13.6 is the binding energy of electron for the hydrogen, which is minus with respect to 0, it is minus. And you have to provide 13.6 electron volt to make it out of the hydrogen atom. So always these numbers are in reference to 0, it is minus, but actually the strength is 13.6 is the strength. That much energy you have to provide to make it ionize. So similarly, this number is negative, but you have to take it as a positive when you are trying to remove the electron from that particular orbit. It means delta E information will be given from this number because a gamma which is emitted, it is equal to delta E roughly. So 279.190 minus 85.529. ठीक है, ये नंबर जो है ना हमें पॉजिटिव लेके चलना है. यहाँ पे रेफरेंस में आपके पास बुक्स में यही लिखा होगा, माइनस लिखा होगा, और कई बार स्टूडेंट्स के हेल्प के लिए एग्जाम में भी वी जस्ट गिव 85 kilo electron volt, which is miss. Means if you see the atoms, they are bounded system, so their net energy is minus. Zero आपका highest possible energy होगा, बाकी सारा minus में, that is a bounded system. So 85 itself is a wrong अंडरस्टैंडिंग कि अगर किसी का बाइंडिंग एनर्जी 85 कहते हो तो रॉन्ग सा एक आंसर मिलता है कि 85 कैसे होगा, तो ज्यादा है, 0 से ज्यादा है, हमने पढ़ा है कि माइनस होता है. इट्स इज ऑब्वियसली माइनस, बट वी हैव टू टेक पॉजिटिव. वी हैव टू टेक द स्ट्रेंथ वैल्यू ऑफ दिस, magnitude value of this. So this will be 179, 193 actually, 193 sorry, kilo electron, and so on for different other. जैसे जैसे आप ऑर्बिट ऊपर की तरफ जाओगे, बाइंडिंग एनर्जी डिक्रीज होती जाएगी, तो T will go on increasing. Got the idea? What wrong we have done? क्योंकि अगर एग्जाम में भी आता है ना कहीं कॉम्पिटिटिव एग्जाम में, तो आपके पास हो सकता है वैल्यू ऐसे लिखी होगी माइनस दिस वन, देन व्हाट इज द electrons energy which is coming out due to internal conversion. So that will be, you have to take positive for that one. So positive लिया, उसको माइनस किया, तो ये नंबर आ गया. ठीक है?
Yes, sir.
Okay. So that is the strength. How much strength, how much energy, means this much energy you have to supply to remove that electron. And once you remove the extra energy which is left over, that will be the kinetic energy of the electron. So अभी हम यहीं पे करते हैं, सिर्फ एक रह गया कि lambda, that is disintegration constant of internal conversion, वो टॉपिक रह गया. Because these two are competing process. जब भी गामा डीके होगा तो या तो फोटोन एमिट होगा या तो इंटरनल कन्वर्टेड इलेक्ट्रॉन्स एमिट होंगे, तो दोनों ही एमिट होंगे, तो दोनों कंपीटिंग प्रोसेस है. तो एनी मोड when follow two different decay mode, then lambda total is lambda of first mode plus the lambda of second mode. रेडियो एक्टिविटी जब स्टार्ट की थी तब मैंने ये क्वेश्चन लिखा था कि लैम्डा ऑफ फर्स्ट प्लस लैम्डा ऑफ सेकंड, दैट इज द टोटल लैम्डा. और नोट्स भी मैंने आपको दिया, तो उसमें चेक कर सकते हो. तो दैट वी हैव टू डिस्कस अ लिटिल बिट, मतलब 10-15 मिनट का और रह गया है. So that we will do in the Saturday class, and we will do the some tutorial and some questions based on beta decay and gamma. अल्फा का हमने कुछ कर लिया, 2 क्वेश्चंस रह गए हैं, वो भी हम डिस्कस करना है, और बाकी 2-4 क्वेश्चन और बीटा और गामा से इंक्लूड करके we will finish off this topic by Saturday, and we will start with the nuclear reactions from next class. No, next means Monday. Okay, so let us first stop the recording, and we will meet on Saturday.